Okay, let's talk about potential divider on page 8. Before that, I'll want you to read the textbook, page 230 to page 231. And after that, you should be able to work out the answer here. Or you can use your prior knowledge about circuit. Get back to me, pause the video now, read the textbook. Okay, so the answer for this is, if you recall what you learned earlier, or you can find from the textbook, the input in total is V in, and we want to find out how much is this for V out. So that means the voltage across R2. Then simply what you can imagine is among the whole thing, across the whole thing, this R1 and R2 are in series. So they would simply share the voltage by its resistance ratio. So if you attend my class, that I told you that it's like you are sharing the cakes or pizza among you and your siblings. So you and your brother or sister is the base of the fraction, and you take the one that you are, right? So this is the answer. And the basic idea of potential divider actually will help you to solve the next question, depending on whether this resistor has a high resistance or low resistance. Then it can take more voltage, or you can control R1 instead to then control the voltage among R2. So this is the idea of potential divider. It's a very practical system. If you're looking for the proof, then I can prove it to you. So first of all, you can apply V equals R. By the way, if you don't want to know about it, that's fine. You can skip it to the next part. But I think it's very interesting to know about it. So V equals IR, you have V in equals to IR. Actually, this R is referring to the equivalent resistance. That means R1 plus R2, which we learned earlier. This is equation 1. At the same time, you have V out equal to I times R2, because the voltage across R2 is equal to the current passing through it. But current, this is series circuit, so current stay the same for both of them. So you don't have to label I1, I2, is all just I simply. And then you just have to multiply with R2. And so by getting these two equations, then basically you can already get the equation by doing I2 divide by equation 1, and then that gets you the V out over V in equal to I R2 I R1 plus R2. Alright, and so you of course you can cancel out the I. As I said, they are the same, and you can simply shuffle the I into this side. Alright, and that actually gets you the equation that we had. So the basic idea is whoever got the higher resistance will get a higher voltage, or vice versa. Okay, for the next part here, if you want to try it, I will really appreciate you can pause the video and try it out. After you try, if you find something that you don't understand, especially about the next part, then you can walk through that with me. Okay, that's totally fine. I got another similar question to you later on. So let's try to do it together now. So for the first part, which will be a very simple question asking you about the what actually NOT gates would do. So you may say, if you remember, it turns 0 to 1, 1 to 0. So you may say it will reverse the signal. All right, or you can say changing the low to high, or high to low for voltage. Okay, either way should do. For a thermistor, it's something that you learned in the previous chapter, and the way that I asked you to remember that is thermistor is a special component which something to do with temperature. From the name itself, you can kind of tell it's something to do with heat, because it's thermal, right? Thermistor. So think about this for normal wire. So maybe I would right here for normal wired, what you can have is when temperature increase, the resistance would increase because of the collision of, like, from the electrons to the atom. The atom will vibrate faster, so it's harder for the electron to go through them, in that case. So thermistor is basically the, well, as we call the special component, it must be different from the normal wire. So the way that it acts is actually when temperature decrease, of course you're going to make it as a full sentence, not the symbol but actually word. Temperature decrease, then the resistance, sorry, I should say temperature increase, then the resistance would decrease. Yeah, that would be easier to say. Okay, so normal wire increase temperature, increase resistance, but this one is opposite, increase temperature, decrease resistance. Okay, so that will be helpful for the next part. Here, this is probably the most challenging question in this chapter, logic gate. And again, try to put your heart to learn and understand that. All right, is the most challenging part. All right, the rest are very easy. All right, I think so far you'll find this chapter is so easy, but this one is a little bit challenging. So let's take a look here. What it said is there is a warning lamp. It asks you how come and why it will switch on when temperature is below, all right, this is a keyword, below a set value. So here we've got a thermistor, and then you just have to answer it. All right, so I think before you actually write the answer, you should make a plan first. So what you can see here is we got actually thermistor is also a kind of resistor, and here this is a variable resistor. You can change the resistance, but of course normally when it's operating, the resistance is fixed. First of all, I think what you have to say, you can see here there are 4 marks. So you really got to have a very good plan to think about, hey, so what are the 4 marks that you are going to write down. So for the first one that I would say is, because the question said below a certain set value for temperature, then what you want to say is when temperature is low. Then of course first thing that it will happen is the thermistor will change its resistance. So thermistor resistance will become high, if you recall what we said earlier, become high. And so in that case, if the resistance of this increase, then you should recall that voltage taken by this thermistor will be high. So imagine if the battery is 12V, then the thermistor probably is going to take up more voltage. Let's say 10 volts. So that means at this point it's already a very low voltage. Already very low voltage. Alright, after the voltage is taken by the thermistor. Okay, so imagine for digital signal, this is a low voltage, or you may call it as 0 in this chapter, logic gate 0. And what happened afterwards is, if you look at these logic gate, this is a NOT gate. So what happened is, if you have a 0 here, then it would turn it to be 1. That means a high voltage. For high voltage, that means it will be able to supply the voltage to the lamp, and so that will switch on the lamp. Okay, so this is a whole logic. So what you can say about is when thermistor resistance increase, then you may say voltage across voltage of thermistor would increase because of what will happen with the resistance of thermistor increase. And in that case, at point P, alright, it's very nice that they gave you the letter here, point P, the voltage will be low, and that actually means it is 0 in that case. All right, you can say in sentence it's 0, and then after the logic gate, which is a NOT gate, and then the NOT gate would turn the voltage to high, and therefore, well, you can see I got more point, but that's fine. I mean, you don't have to write down the numbering, but then it's always better to write more. To high, and that voltage, high voltage, would simply turns on the warning lamp. Okay, so this is the whole logic. Number 2, it asks you the effect of changing the resistance out. That means the variable resistor, apparently when you change this, then the the ratio between thermistor and the variable resistor will be different. So imagine if this increase, then thermistor has to be the resistance has to be even higher to switch on the light in that case. So what you can say about is for the very basic level, then you may say, since it's 1 point, then you may say it will change the activating, or you can say the set value, according to the question is at the set value of the temperature. Alright, so maybe beforehand it was temperature. So maybe beforehand it was say 40 degrees Celsius. Now it's 60 degrees Celsius. For your practice, I'll give you a chance now, a question right now. Let's say you are the engineer, the electrical engineer. You want to design the street lamp so that when the sky is getting dark, it will switch on the street lamp automatically. In fact, this is exactly how we do in Hong Kong as well, or I'm sure most of the cities around the world. It's not about the smart street lamp. It's has been done many years already. So if you see something like a box like this, here, like the window here, actually there is a light sensor. So it detects the light inside, and that actually control. So imagine the street lamp is not controlled by time. You don't find the street lamp switch on or off at a definite time. When there are times, let's say it's raining, the street light also switch on. So it's something to do with the control by the light intensity outside in the skies. So think about how the circuit should look like. One challenge for you is you are not allowed to use any logic gate. So how could you actually make it? Think about it, pause the video, and get back to this video later on. Okay, here is a circuit that I drew. In order to get you understand more, this I can already tell you that is a wrong answer. Okay, this is wrong answer. So let me show you how. First of all, I think most of you should realize that in order to detect the light, you have to use the light-dependent resistor, LDR. And let's recall the property of these first. For this, when the light intensity increase, the resistance will decrease. Okay, you have to get this correct first. All right, otherwise you will mix the whole thing up. The next thing is, in that case, when the light is on, that means, or I should say the other way around, when the sky is dark, then resistance will increase. So in that case, when the resistance of this increase, then the voltage of this will increase. So maybe I try to put it as a point form. So when it is dark outside, then the voltage across LDR will increase according to what we understood, and therefore the voltage of the street lamp, okay, they are in series. In this, again, this is a wrong design. The street lamp will have less voltage. So if you think about the what happened is, when the sky is dark, actually the street lamp would not be switched on, it's actually switched off. That means on the other case, when the sky is bright, then voltage of LDR would decrease, and that actually make the voltage of the lamp increase. That means it's switching on the lamp. And isn't this ridiculous? That means you switch on the lamp when the sky is bright. So this is exactly opposite of what you want to do. So that's why I said this is a wrong example, but through understanding this, you can learn more about the logic gate itself or the circuitry itself. Let me show you the correct answer right now. Okay, so here's the correct answer. We have LDR here and also the street lamp here. So take a look here. What you may see here is you can imagine this as a whole is a resistor, but then it will change according to the brightness of the sky. And so here's a variable resistor which you can change its value so that you can kind of adjust the intensity, or if you don't like it, you can just make it as a normal resistor. It's also fine as well. So what you can say about is, when the sky is dark, okay, you can write full sentence, of course. Then the LDR resistance of LDR would increase in that case. So in that case, the whole resistance across this, even though this is a parallel circuit, then the equivalent resistance of these two will still increase, and that actually make the whole voltage across this V1, let's say, and this is V2. V1 will actually increase because of the equivalent resistance increase, if you recall the potential divider relationship. So in that case, you will have more voltage across both LDR and also the street lamp. So in that case, the voltage across the lamp will increase, and that means switch on the lamp in that case. Okay, so this is one of the possible way to switch on the street lamp when the sky is dark. But of course, this is not the most efficient way because there are so much energy wasted to the LDR and also this resistor, and in fact people don't actually make this system because again it's not energy efficient. But this is one possible way given that you don't have logic gate or any other smart devices.